we'll continue our discussion of infrared spectroscopy, looking at some different functional groups, moving out from the different alkyl and alkenes and alkynes that we've seen before, and start looking at some different functional groups, because that's where IR really becomes useful. Most organic molecules have CH2s. Many have CHs that come off of double bonds or triple bonds. So when we start utilizing IR, we really need to utilize it to find the different types of functional groups. Alcohols, ketones, esters, that's where we can get a lot of utility from IR. So we'll begin looking at alcohols. Now, alcohols typically fall somewhere in the area of 3,300 reciprocal centimeters. These are very, very far to the left, and they are typically broad. So these are very strong signals, and that should make sense because the oxygen-hydrogen bond is very polar. So when we look at the spectrum of 1-butanol, we see that the OH stretch right there is very clear. Moving on, if we take a look at an amine, amines are NH groups. Often we'll think about them as NH2s, NH with some other group there, or even a nitrogen without any hydrogens on them. So if a nitrogen has a hydrogen on it, typically we see those peaks come out around 3,300 reciprocal centimeters, and they are broad. This makes it very difficult to discern between an amine and an alcohol. You can make guesses as to whether you have an amine or alcohol, but it's not always clear. So if we take a look at propylamine, we start to see that NH stretch, which is broad, around 3,300. Now in this particular instance, when we're dealing with propylamine, we're talking about two nitrogen-hydrogen bonds. And these guys can be distinguished because you have the nitrogen-hydrogen stretching. Now they both can be stretching out and back at the same pace, or they can be stretching asymmetrically. All right, so that is a different type of stretch, where the H in this case is stretching out, and at the same time the other H is stretching in. So there's two different varieties of stretching, and that's why we see two peaks right there. So that can be a bit of an indicator, but that's not always the case. When we look at dipropylamine, that is a different situation. Dipropylamine, we do see a broad peak here, but that it's not so clear. There's definitely a broad peak there. It's not as big, but it's only one peak. It's not two. So you can't always tell an amine from distinguishing an amine from an alcohol in IR. There are other ways to do that, namely mass spectrometry, as well as NMR, which we'll learn a bit later. When we move on to alkynes, we haven't really talked about where these guys come out. We talked about the sp3s are going to be less than 3,000. The sp2s are going to be greater than 3,000. But alkynes are a little bit different. Those are around 3,300 reciprocal centimeters. Now the difference between an alkyne and an alcohol or an amine is that these peaks are sharp. So if you see a sharp peak around 3,300, that's a sign that you probably have a CH stretch from an alkyne. One other giveaway for an alkyne is that you have the CC triple bond absorbing around 20, usually around 22, 2,300, but we'll say 21 to 2,300. There aren't many things that absorb down in that region. Only a CC triple bond as well as a CN triple bond, which we'll talk about a little later. But that is the only thing that falls in that region. So here's another example of an alkyne. Now this is 4-octine. So I want you to take a look at the structure of 4-octine. 1, 2, 3, 4. So this is 4-octine. Notice this is a completely symmetric alkyne. It does not have any CHs, so therefore there is no CH stretch from an alkyne. But also notice there's no CC triple bond stretch. Now that should make sense as well, because what did we say about bond polarity? The less the polar bond, the less you see it in IR. And there is a symmetry to this molecule which prevents it from pulling on one side or the other, so nothing shows up. So IR can be very deceptive at times. Clearly there's an alkyne here, but we see nothing in the IR to indicate that that is the case. So you always have to be very careful about what you see and what you interpret from IR. Moving on to nitriles, we talk about the CN triple bond. Now this has a much greater polarity, and these almost always show up around 22 to 2300. Same region as the alkynes, and a very clear peak indicating the nitrile. Carbonyls, again, are a big part of IR. They are highly polar due to the carbon-oxygen double bond, and we see that with the bond polarity. So these show up very strong in IR. And the substitutions on these carbonyls will affect where they come out. And it allows us to distinguish between these various functional groups. So we have the aldehyde, we have the ketone, we have an ester, we have a carboxylic acid, amides. There are a variety of different functional groups that contain a carbonyl, and we should be able to distinguish all of these based on their IR. It's not always easy, but we can do it. So we take a look first at ketones. Ketones usually absorb somewhere in the area of 1710 reciprocal centimeters. That can vary depending on the types of substitutions that it has, and it is very strong, and we see that right there. So this would be cyclohexanone. So that would be a 6-membered ring with a ketone right on it. Okay, so very strong. When we move on, we look at another ketone. This is acetophenone. Now this molecule is similar, but the ketone is directly connected to this conjugated system right here. So the ketone is in conjugation with the ring. And remember what we said about conjugation. What it does is it spreads electron density around. And if you spread electron density, you lower the frequency. And that's what we see here. The ketone stretch is around 1685 instead of 1710. So that's what happens when you start putting ketones into conjugation. Oh, so there it is. Conjugation lowers IR frequency. When we take a look at the various functional groups that are put on the ketone, as we said, 1710 is your standard, but once you start putting some pi systems in there, we lower further and further. Okay, so keep that in mind. If you see a conjugated system, it will lower the IR frequency. Aldehydes, those fall very similar region, around 1700 for them. So you can't distinguish an aldehyde from a ketone by that carbonyl. But it also contains this carbon-hydrogen bond right here. And that is unique to the aldehyde. And those peaks show up around 28, 2700. So that is unique to the carbon-hydrogen bond of the aldehyde. Okay, but again, it still has the carbonyl peak at 17, in this case 1720, so around 1700. Again, more examples of aldehydes. We still see the 2800 and the 2700 and the carbonyl stretch. We're going to look at esters. So those are those carbon-oxygen double bonds that are directly connected to an oxygen. Now this, what we start to see is the electron withdrawing effects of the oxygen start taking over, and we start to get a very strong bond polarity here. And so these peaks tend to be very, very strong. And so we have this peak coming around 1740, a little bit higher than the other ones, but still these are very close to where a ketone or an aldehyde. Typically, though, where we also see peaks are around 1200 to 1100 in the fingerprint region, and those are usually associated with CO single bond. So if you see peaks around 1740 as well as 1200 to 1100, often that can indicate an ester, or it may not. It could indicate a ketone and something else in the molecule that contains a CO single bond. So again, they can be very misleading, but you usually do see the peak around 1740, 1730, that area. Amides are very unique, and they are a bit lower than all the other carbonyls. And the reason why is because that nitrogen is very readily donated into the carbon of the carbonyl, and what you get is this resonance structure. And when you get that resonance structure, basically what you're doing is you're looking at this as a CO single bond instead of the CO double bond. And remember, when we make it a single bond, we decrease the amount of energy needed to vibrate that because it's less strongly held together. So what that means is it takes less energy, and therefore it shifts the frequency to lower frequencies. So we're talking about 1630 to about 1680 for the peaks associated with an amide. Now, if your amide contains hydrogen, you may also see an NH stretch. So butyramide would be this. We have two NH stretches, and we see that with our two peaks down in that region where we usually see NHs. So an amide also contains an NH, and it can show up in the IR. Another example here of an amide, again, 1650. We're seeing that, and we're seeing our NHs show up there. One slide that I didn't show, which we might talk about, is we're going to talk a little bit about carboxylic acids. These have peaks that show up again around 1700 because it has the carbonyl. But it also contains an OH, and this is a broad peak that can range anywhere from 3000 to 3500. And it is very, very broad. So again, maybe you have a ketone and an alcohol. By IR, it is not easy to distinguish these two. That is why we use other techniques such as mass spectrometry and, again, NMR, which we will cover and will be a very important part of this upcoming test. So we're going to end the IR lecture there, and we'll pick back up with mass spectrometry in our next lecture.